Hey guys, today we're going to talk about a few things related to electricity and magnetism, but we'll start with kind of the old electricity circuit stuff and how it applies to things in our home. So here's a typical energy bill from the electric company, and you'll see here that the usage is measured in something called kilowatt hours. We might have talked about this once before, but for your bill part, they usually break it up into tiers, so you pay more money if you use too much electricity. So you can see this person, they used up to this amount, which was 328 kilowatt hours, and paid 19 cents a kilowatt hour for the first 328. And the next 34 kilowatt hours, they paid 25 cents. Okay, so if you end up way over here, you're paying more and more. You're paying 25 cents per kilowatt hour, and if you get all the way up here, you're paying 44 cents per kilowatt hour. So they're trying to encourage you to not waste electricity. But they measured that energy, that electrical energy, which really comes, it's really if we think of it like from a battery, we'll go back to the battery example, we're going to call it an electric potential energy with an E there for electric potential energy. They're measuring it not in joules like we normally would. They're using something else. So we're going to go back to something from a while ago. We said that a change in voltage. Remember voltage? We gave an analogy like it's the pressure in a water pipe. Okay, it's not just an analogy. It's not really quite like that. But we said that the definition of voltage was a change in potential energy. In this case, it was electric potential energy per charge. Okay, so if we have a battery and a circuit, we could have positive charges. If this is the positive side, positive charges here would go down in voltage from some, like if this is a 9-volt battery, they'll go from 9 volts down to 0 volts. So they would have a negative 9 change in voltage, and some positive charge would give us a negative change in potential energy. Okay, it's really minuses, electrons. Okay, so they would go a minus charge here. This solving for the change in electric potential energy, they're going to go up from the negative side to the positive side. So they'll go up 9 volts. And it doesn't matter. The change in electric potential energy is negative either way, which means the charges are losing energy, which is what they want to do kind of naturally. Okay? But we're going to take this equation here, and we're going to solve for the change in electric potential energy. So how much energy gets used? Okay? It's going to be Q times delta V. All right, and this would be in joules because this is coulombs, and this would be in volts, but volts are just another name for joules per coulomb. The coulombs cancels out, and they could give you your answer in joules, but they don't. They give it to you in another form, and that other form is going to actually show us something about electrical circuits. Okay, if you think about like a light bulb is measured in watts, right, which is how much power it's using. Okay, so I'll just write, it's a capital P. I'm going to write power here just so you know what it is. Power is a amount of energy per time, right? So what we're going to do is it's the energy here. So how much energy do these charges lose per time? Okay, is power. But we're going to plug in Q times delta V over T. Okay? However, what's Q over T? Well, if we want the total power, right, the power used by this entire circuit over this amount of time, like 10 seconds, we'll plug in this Q total. But Q total, how much charge is moving by in a given amount of time, that's the definition of the current. And I'm glossing over one small thing, but it still turns out to be true. In real life, it's not like charges are coming out of here and moving around. It's like a chainsaw, right? There's charges all along this, and they're all moving at once. But this is still true. This works. And so the power is equal to this here is the current times the voltage. Okay? And that is an equation that works. If you have an ohmic resistor and a resistor that obeys Ohm's law, you can also say, well, I is V over R, right? So you get V over R times V is V squared over R. Or you could replace the V with V is IR, plug in IR there, and you get I times I is I squared, times R is I squared R. And we didn't talk about these, but this is true, but if it's an ohmic resistor, these guys are also true. Okay? What the power company is doing is they're not really doing this or this. What they're doing is they're saying they're going to rewrite this equation back up here. Okay? So they're going to take this, I'm just going to rewrite it down here. Its power is equal to the change in potential energy, electric potential energy over time. And they are they're giving you this energy, right? And it's not really a battery. They're, generating electricity at the power plant. But however much, energy you're using up, they're giving you. So if we solve this for the change in potential energy, it's power times time. And power is energy over time. So joules per second, which are called watts. So this would be in units, it would be watts times seconds. And they say, that's still joules. This is joules per second times seconds. And the number would just be too big. You'd use like just a huge number of joules in a month. So they give it to you in kilowatt hours. This number is 1,000 times bigger than this number. This number is 3,600 times bigger. So 1 kilowatt hour, convert kilowatts, 1,000 watts, and 1 hour is 3,600 seconds, gives us 3.6 million joules. Okay, so this person, this family that used 362 kilowatt hours in roughly a month, you'd multiply that number by 3.6 million joules. So 362 times, come on, numlock, 362 times 3.6 million. Get the right number of zeros in there. Yep. And that's just a hard number to even look at. It's 1.3 billion joules got used in that month. So people don't like those types of numbers. So instead, it's much easier to remember something like 362 kilowatt hours that were used in that month. So that's why they use that. You will notice something else here as well. If I go up here, it says the service voltage here is 240 volts. Okay, and we'll get to that in a second. A lot of people talk about it being 120, and it usually is 120. But you can get up to 240, and I was confused about this for years, but let's start with the 120 number first. We're going to take this P equals IV, and we'll probably be easiest to think about it as in a V squared over R term here, actually. So I'm going to take that just to give us some room. P is equal to IV is V squared over R if it's an ohmic resistor, and I squared R. We're going to pretend like your house is a pretty ohmic resistor so that we can use this one. So when people talk about voltage in your home, the voltage is AC, right? So it goes something, I'll just draw it. It's like a sine or cosine wave or something like that, that we don't really care where it starts and finishes, and whether it starts right there exactly, but something like this. Okay. So sometimes the electrons are pushed in the positive direction, sometimes they're pushed in the negative direction, all along here. And people think that this right here is 120 volts, but that's actually not true. Okay. What the 120 volts is sort of like an effective, I should put V. It's like an effective voltage if it were DC. Suppose that the voltage were DC, okay? And the voltage were the same the whole time, okay? We would get power from that voltage. Well, this is really going up and down and up and down and up and down. So this effective is 120 volts if it were DC, but really it's going above 120 and then down, and it is actually going in the negative direction. But we don't care whether electrons are going positive or negative. But really what we want is not V, but V squared, okay? Because the power has to do with V squared. So what we actually want is not V, we want V squared, okay? So we'll take this 120 volts and square it. But the V squared would go like this. When we square this negative, right, it comes back up as a positive like this. I'm trying to draw these, identical, but I'm not. Okay, so the average, okay, in here, sometimes the voltage is higher than 120 squared. The voltage squared is higher than 120 squared. And sometimes it's less, but the average is 120. And if you know calculus, you can actually work this out. But it ends up being like this. The V, and they call it RMS, which stands for root mean square. But basically, it's the effective DC voltage, okay? Kind of like if you have a wire and you hook it up to something that's AC, how hot will it get? Well, what DC voltage would produce that same, how hot it will be? It's actually true that the lights that we have actually, because the voltage is AC, even regular old like wire, they're called incandescent light bulbs, that have a glowing wire, they can actually get brighter and then dimmer, and they're like dimmer and then brighter and then dimmer and then, still a little bit brighter, a little bit brighter, a little bit brighter, a little bit dimmer, a little bit dimmer, a little bit dimmer, a little bit brighter, okay, like that. But we just don't notice it because this is 1/60th of a second. So they're getting brighter, dimmer, brighter, dimmer in a 60th of a second, and we don't notice. Unless you got like a real high-speed camera, you're not going to notice. So there it is again. You can watch this. The bulb actually, because it's AC, whether it's 120 or 240, this bulb is actually getting brighter and darker because when the voltage gets higher, it gets brighter. Even when the voltage is 0, it's still glowing because that piece of metal in there just doesn't have time to cool down enough to stop glowing. But that's just a picture there for you of AC. Okay, so the effective resistance is 120 volts, and the effective resistance takes the peak resistance, okay, and divides by root 2. Just trust me on that when you do the calculus. So V peak is the V RMS, or the V effective, times root 2. Okay, we just multiply both sides by root 2. Sorry, that's a root 2. So we are told that this is the V effective is 120 volts. Okay, that's often quoted. And if you multiply that by root 2, let's do that. So 120 times, and this way, this one is just 2 square root, and it's about 170 volts, okay, is the peak. So this is 170 volts, okay, so this up here is really 170 volts for this peak, okay. I'm not doing the calculus on all this, and this would be negative 170 volts, okay, so the peak voltage is called 170 volts, so V peak, it's written just VP oftentimes, is 170 volts, and sometimes people talk about the peak to peak voltage, which is from the crest up here to the trough down there, is going to be double that, right? 170 up, 170 down is 340 volts difference between the peak there and the peak there, okay? That's the normal thing that people talk about in their homes. So why did this energy bill back here say 240 volts? Well, let's go on a little field trip here in my home. Okay, I have my multimeter here. I'm going to turn it on to a voltage setting here. Hopefully you can see the V. It defaults to DC, so I press select, and hopefully you can see here there's this little squiggle right above my thumb that is supposed to be for AC, okay? And I'm going to take this, I'll show you let's see if I can do this like this. And I'm going to put now you don't do this at home, okay? I'll do this. I know what I'm doing. So I stick this in here. It's just bouncing around really. It still doesn't really have any voltage. And I'm going to stick this in there, and you can see it says about 120 volts. Okay. And that's normal usage. Normal plugs are 120 volts. Okay. How do we get more than 120 volts? Okay, so we're over here by the dryer, and some big appliances that take a lot of electricity and stuff and require a lot of electrical power, they get 240 volts, and we'll talk about later how that works. I don't even like pulling this thing out because it's more voltage, but it has this strange looking connector here. Okay, looks very different than everything else that you would have in your home, so that you can't accidentally plug a normal thing like this into this socket over here. Okay, and if these prongs are so long actually that I can't even get my leads back there far enough into it to measure the voltage. So I'm going to do something like this and be very careful. I'm going to plug this in most of the way. I'm not going to get my fingers anywhere close to those things. I'm going to see if I can set this down here. Well, I can probably do it like this. Okay, so get this one touched over there and that one touched over there. There we go. It's not working. They're not all the way in. Oh, there it goes. I touched them. Okay, so 240-ish volts. Okay, so this is getting 240 volts, and I'll show you a little bit more about that. So we're out here at my breaker box, okay, and so you can see here that some of these, the circuit breakers are tied together, right? And there's two of them for one. So this says cooktop. Somebody else did this before we bought the home, so that's probably like the electric stove, and it has two of these tied together. So when you flip them together, they turn on and off together. But these things that have two breakers in one, I believe, these provide 240 volts total to the appliances. The ones with just one have 120 volts, which normal outlets in your homes use, right? 120 volts in the normal outlets. Okay, I didn't understand for a really long time is that instead of actually only two wires coming into your home from the transformer, there are actually three. There's two what they call hot wires and a neutral wire, okay? And so here they are coming in from the the power pole into a transformer. And so if you take a look at this transformer here, there are three wires, okay? So these are the wires coming from the high voltage, okay? Here's the high voltage wires coming down from above, right? Farther away from us, the high voltage ones. And here are the ones that are come out lower and go to our home, and there are three of them. Okay, so here they are, three coming into like your electric meter that says how much electricity you've used. And here is the breaker box. And if we just advance forward here a little bit, so here are the two hot wires, okay, coming in, and they come in on opposite sides of the breaker box, okay? And those, the two hot wires, which they've drawn right here, and they're going to set this up to a neutral wire here in a little bit. So there's the neutral wire going like this, and usually your regular appliances, they only use one side, either the left side, 120 volts, or the right side at 120 volts. So now they're using the right side. So these are both 120 volts, okay? Because what they're doing is when you are using only 120 volts, you're only connecting across the neutral bus bar, they're calling it. And this hot wire, if you're like on the right side of the control panel, or the neutral and the other hot wire, and you're only using half of these turns, okay? So if you were to get out a multimeter and measure from one side to here, that's 120 volts. If you do the other side, 120 volts. But if you go across these, now you're getting all of these turns. So if you remember, in this transformer, the number of loops matters. So when you're using from here to here, it's double the number of loops, so double the voltage. Okay, so when you go back to the breaker box, most of the time, what you're doing, let me advance it here to here. Normally what happens is, and in the middle of drawing this wire, let me let it run for just there. Okay, you've got a light switch. All right, and so here comes one of the hot wires to here, and we're just using the right hand side of the breaker box. Okay, and then this hot wire goes to a switch so you can turn the light on and off, to the light, and back to the neutral wire. So we're going from the right side to the neutral is 120 volts. Okay, and that's what we usually do. When you get something with using both hot wires, you get this circuit breaker that is, a double looking one, and it's going to go across both. Okay, so do you see how this side here is touching the right hand side of this, which is touching the right hot wire, and this left hand part is touching the other one, and you're not going to use well, you can still use the neutral if you want, and so this kind of looks like what I had. It's pretty similar, a little bit different than what I had for my dryer, but what they're showing here is if you were to take this and connect from hot wire to hot wire, this black one is going, this red and black coming out here, from there to there is 240 volts if you want 240 volts. From here to here is 120, or from there to there is 120, because this is just like going from, this black one is attached to the left hand part over here. So it's like going from the black is touching the left, and this white is touching the neutral bus bar. So you could either get 120 volts or 120 volts or 240 volts, depending on what your appliance wants. But this is set up, with a weird configuration than our normal plugs, so you can't accidentally plug, your laptop or cell phone into the 240 volts and fry it. Okay. And now we actually know enough to understand how the circuit breaker, one way a circuit breaker can work. This is a bit simplified, but imagine inside the circuit breaker you've got something like this. Okay, here comes a wire. Okay, it's going to come out over here, but in the middle we're going to have this switch here. Okay, all right. So like, if you pull it, if you were to flip the switch, open the switch, like a switch can be closed or a switch can be open, right? And the electricity can't get through. Okay, but before the switch, we're going to do this. We're going to bring down our wire like this. So here comes the electricity coming in. We're going to go like this, come over here, and then make these loops, okay, this coil, like that, okay? So under normal operation, what happens is electricity passes through this, right? And it makes a solenoid like an electromagnet, but this has some spring in it, and this stays connected. But if this current gets too high in here, then this electromagnet, although the current is flipping, it's flipping back and forth. So this is becoming, north is this way, and then north is the other way, and south is this way. It doesn't really matter. This magnet will be getting stronger, weaker, stronger, weaker, stronger, weaker. But at some point, if it even, in its strongest magnetism that it's getting, if the current in here is ever too high that this becomes a strong enough magnet at some point, this thing here is made of like iron, and even though it has some spring, say holding it, if this becomes a strong enough solenoid, a strong enough electromagnet, it can actually open that switch and pull this piece of iron downward, cutting off the circuit. The electricity can't get through. So remember we talked about fuses. Fuses are much more simple. They just kind of look like this. This is a piece of metal and a piece of metal, and then inside there is a thin wire. And if the current through there ever gets big enough, this thing burns up, and there's a gap, right? And the electricity can't flow. A circuit breaker opens a switch, and some of them use an electromagnet, a solenoid, to open that switch when this current gets too big. And what you're going and doing when you go to the breaker box is you're like pulling this that bar back over here, and you're shoving this thing back into place. Okay. Now, if there's still a problem, if there's a short circuit in your, some two wires that aren't supposed to touch have touched, or if you have still like, 5 appliances on the same part of your house, it can just pull this down again. But that's how that works. And then sometimes in your home, they have something like this. You've got a plug. and then in the middle there are these little like test and reset things, yeah? And this is called a GFCI, ground fault, I forget what it stands for, circuit interrupter, there it is, ground fault circuit interrupter. And the idea is, what it does is it measures, and I'm trying to think exactly how it does it, but this is just something I came up with as like a guess. Here's your other wire, okay? So this goes over to your circuit, right? Your toaster or whatever. And then this wire comes over here, and suppose it goes up and makes another electromagnet, okay? When the current through these should be the same all the way through. Now the current's flipping back and forth, but the current should be the same. So when this is a strong magnet, this is a strong magnet, and this thing gets pulled equally in both directions, this piece of iron here, and it doesn't move, okay? I'm guessing at this, I'll be honest. I'm guessing, I just came up with, how would that work? And I'm coming up with this. This thing says, what happens if somebody is being electrocuted currently, okay? You're not a great great conductor, right? You're kind of a mediocre conductor, but let's suppose that you're getting electrocuted by sticking, a screwdriver into one of those, okay? And the electricity is not going back down through the other wire. It's going, and I'm going to keep it simple here, but going to ground, they say. Anyway, what this does is it measures if you're touching like over here, right? You touch that wire, okay? And the electricity, instead of going through here and going around, it's going through you. Oopsie daisy, right? And you're getting electrocuted, and the electricity is going through you to the ground, and the ground is not a great conductor either. And how it gets back to the circuit is complicated. Back over here, there's a wire to the ground because of lightning bolts and stuff. But it could pass through you, pass through the ground, which is a bad conductor as well. But the idea here is this. This part of the circuit is getting electricity, and this part is not. So this will still be a magnet, or could be a magnet, right? At certain parts in the cycle of the electricity. This will be a magnet, and this is getting like no current. So it's measuring these two currents, and if they're different, it pops open the switch. Okay? It's saying something is wrong in my circuit. The current over here should be the same as the current over here. And this is much more local. It's very close to this, and it's supposed to shut off the circuit fast if you start getting electrocuted, because it's close in the line, and it doesn't have to have a huge amount of current for it still to trip this. Okay, imagine there's like no spring in this. It's just very easy to move. If these currents are different, then it's going to open that and hopefully save you. There's another one which deals with, there's another tool which deals with if you have two wires, because the wires usually, they're going through a cord like, like a mouse. There's actually two wires in there, right? And they're very close together. If something happens inside there where some animal starts to chew through them, or somebody puts a screwdriver into the wall, and actually I'll draw two full wires here, and the insulation gets like scraped off. Okay, so this is rubber, and somebody puts a drill through the wall and scrapes off the insulation. It can make an arc, like a little lightning bolt between the two wires. And there's something else, arc faults, I think it is, arc fault circuit interrupter, and it's just similar to this, but it's not, it's worrying about this making arcs every time the voltage goes high. It's going to make a little arc, and the voltage won't keep going up like it should. Okay, it'll be like, make an arc. Okay, and this thing watches out for that, because sparks in the wires, a little lightning bolt in the walls of your home, if somebody drilled through and scraped these, they didn't drill through them enough to break the circuit, but they drilled through and exposed the bare wire here. It can make lightning bolts called arcs in your wall, and that can start a house fire. So they have these in like bedrooms, or connected to bedrooms and things like that. And anything close to water, they make you put in a GFCI. So bathrooms and anything that's close to a sink in your kitchen, they have to have one of these guys to try to protect you even better, because you're not a great conductor. So a regular circuit breaker back, that I showed you in the video, you'd be long dead before those things trip, basically. If those things trip because you're getting electrocuted, you're pretty much toast. So these things are because they're like 15 amps, and 1 or 2, probably like 2 to 5 amps will kill you. So, well, you're just bad resist. Yeah. Anyway, these guys are providing safety in a different way. So that's why you have those. So here's their little video of somebody putting a nail and like scraping off the insulation between the two wires so that it can make an arc across these two wires and burn down your house. And I'll put a link to this video. You don't have to watch it, but I found it really interesting, and it's the engineering mindset, and they've got a whole bunch of videos about electricity and stuff. But I did not understand. Maybe I understood a long time ago and forgot, but I didn't realize that there are 3 wires going into your home. And how you could get 240 volts out of it. And the other thing I will show you is on the normal outlet. Okay, so well, that one you can't see the outlet. On an outlet, usually one side, one of these holes right here is bigger than the other one. I think usually the left-hand side is bigger. The left-hand side is connected to the neutral wire, and the right-hand side that's smaller is connected to the hot wire. And there's a reason for that goes beyond even the scope of this. It sounds crazy, but it's actually possible for there to be less current through the neutral wire because it can have a current flowing from this loop and a current flowing from this loop. And since the currents want to kind of be, if the current through this wire is going this way, right? It's going, say the current in these loops is going up, okay? Then this loop is going to be having a clockwise current, so it's going to the left through this wire. But if it's going up, then this current wants to go this way, clockwise, which is to the right through this wire. And you can actually have less current going through your neutral wire than either of these. In fact, yeah, so there's a reason there's a neutral wire there. I never understood if it's AC, why is there a difference between the left-hand side and the right-hand side? And it's because it's not just one circuit going on. There's actually these 2 circuits. I lost it here. There's actually 2 circuits, so you can get 240 volts for some of your appliances. So hopefully that tells you some things about your home and how things work and why they work. Hope you enjoyed.